important highlights here for people who want to know what you can do with MIRI. So you saw MIRI is over here. This is the field of view. MIRI is over off to the side, far from FGS. And the coronagraphs are up and down the left side of MIRI in descending order of wavelength from the top to the bottom. We have the 23 micron LEO mask, which is a round mask, a round occulter similar to the ones on NIRCam. We have the 4 quadrant phase masks, 15, 11.4, and 1065 at the bottom of the detector. And on the right side, you can see the armature that the mounting bracket that they're on. So these dark regions, if you see my mouse, these dark regions are actually opaque. They are blocked by metal and no light goes through. And then you have the imager field of view over here on the right. There are 4 coronagraphs and they're optimized for different sciences, Julian explained. In fact, I stole this slide from him because I really liked it. We have so there's a model spectrum of a cool planet down here. We have NIRCam at short wavelengths, and then all the way at the right, we have the MIRI filters start to come in. There's the 10.6 micron filter that is designed to detect an ammonium absorption feature. And if you can measure its depth by also taking the 11.4 micron data, which should be at the peak. If you take the difference between the 11.4 micron and the 15.5 micron, you'll get a measure of the slope of the tail of the planet, and so you can get a handle on its temperature. And then way out over here, the 23 micron is optimized for disks. It's very broad. The inner working angle is 3 lambda over D, opposed to 1 lambda over D for the 4 quadrant phase masks. So you're not really going to get anything really close, but also the PSF is very broad at that wavelength anyway. So this is the science case. This is what these particular filters are designed to do. Here's for reference later. This is a table taken from Anthony Boccoletti's program. Anthony Boccoletti's paper explaining the design of the coronagraphs that he wrote in 2015. His team were the ones in charge of designing the 4 quadrant phase masks. And so this is the schematic of the 4 quadrant phase mask at the bottom, and the reason, and there's an SEM image of what it actually looks like on the right. And the reason for showing you this is to sort of explain how it works, and explaining it drives a lot of our operating practices, especially our high pointing precision requirement. So if you center your PSF in the middle of these 4 quadrants, then you'll get a 180-degree phase shift on opposite sides, and they will destructively interfere when you re-image it on the focal plane where your detector is. But because of this, you really have to nail that center of the coronagraph. And our design spec is to have the TA, the repeatability. We want the standard deviation of the pointing to be, something within 7 to 10 milliarc seconds. And so if you think about slewing a 2-story building on top of a tennis court with 10 milliarc second precision, it's quite a feat that they are able to pull it off. It's actually pretty good. So this is a summary on the left side of our pointing precision. And I have 3 circles at 5, 10, and 20 milliarc seconds. And very few, sometimes you get unlucky, but by far most of our TA happens within the 10 milliarc second circle. And so we're performing within spec. We're very happy about that. This is the main contrast improvements that you get are from having a well-matched PSF to do with PSF subtraction, and that a lot of that depends on the repeatability of your pointing. And so this is a good sign. So the other aspect of the performance is how it's the uncertainties on your photometry. So the photometric calibration program puts bright sources in the corners of the array, so they're far from the nulling center, and about 1 to 3% uncertainties on the photometry for bright calibration stars. When you're talking about close-in companions that you have to do a lot of processing just to see, people report in the literature, it's more like 3 to 5% uncertainty. So this is sort of precision that you can expect for your science. The contrast also is, something that we all care about, and I've compared here a plot on the left from commissioning. These are the reported contrast curves at the end of commissioning, and then on the right we have a science paper from someone who spent all of their time pushing the contrast limits on this particular target. So and they also compare different strategies. So on the left in the commissioning, you can see you can see a comparison between having no PSF subtraction at all, so just the natural fall off of the PSF with separation, against just simple one-to-one PSF subtraction. So you take one reference image and you subtract it off, and then also versus using a library, the full principal component decomposition of the PSF to model your science target. And so we're getting about 10 to the minus 4 contrast as our 10 to the minus 5 is the limit, more or less at 10 and 11 microns. At 15 microns, it's a little higher because that's when the thermal background starts to dominate, and so you're really more background limited at that point. You can beat that down with exposure time if you want. So one interesting caveat here is that most of the so there's a large gap here between the raw and the subtraction PSFs. We think what happened in this case was that a tilt event, so one of the mirror segments moved between the science and the reference observation. And so this is, these things can happen. This is when, if something is wrong in your data, you want to go look at the OPD maps that Julian showed that SDPSF can get for you when you're troubleshooting. And that's right. But if we go over to Mathilde Malin's paper on GJ504b, you can see that she is getting about 10 to the minus 5. She almost reaches 10 to the minus 5 contrast at 10 microns. And what's nice about this is that she compares different PSF subtraction techniques. There's some with only use contemporaneous PSFs, and there's some that use the entire library of all the reference PSFs that have been taken in the history of web operations. And those give you the best contrast because, despite tilt events aside, the mirror is very stable. We have really great wavefront control. And so by leveraging the power of this library, multiple PSF, to really match the position of your star, you can dig really deep. And with the 4-quadrant phase masks, you can go to very small separations as well. So we have different observing strategies. There's one-to-one PSF subtraction, multiple contemporaneous reference images, archival reference images. You can also use angular differential imaging, although with the roll angle of 15 degrees and at 1 lambda over d, it's a little challenging, but there are important use cases where you want to make sure that you get ADI. And so on the right, we have Anthony Boccoletti's paper on HR 8799 that Julian showed you. The top row is unsubtracted, and you cannot see the companions. You cannot see the HRD79 planets. The bottom row with reference differential imaging and the contemporaneous library, we recover all four. Below that, we have Aaron Carter's paper, who has a nice demonstration of the different strategies, both with NIRCam and with MIRI, of what you get when you do ADI, RDI, or you can even combine the two. And so these are important strategies. It's important to think about when you're thinking about your science case. For example, if you know where the planet is, maybe RDI is enough, but if you don't, if you're doing a blind search for planets, even if you can only get 15 degrees of roll, you might want to prioritize that in your time, because you want to make sure that you're not, to detangle your speckles from your planets. And so these are important to think about. It's important to think about your strategy when you're planning your proposal, your program. So once you plan your program, what do the data look like? So Julien gave you an overview of the mast interfaces. So what happens is the data come down from the telescope, and we process the raw data through several stages and make all the data products available to you. Goes from the ramps to slopes, where we take the 4D cube of groups, integrations, exposures, and we fit a ramp to the groups, so we get a slope that counts per second. Then we calibrate the ramps of data number per second to physical units, and then we do some post-processing as well, which for coronagraphy, everyone has their own post-processing pipeline, PSF subtraction pipeline. Ours is like a kind of a quick look to make sure that things did right. You'll want to do your own, but you can certainly start from the stage 2 files if you like, or spaceKLIP has all these incorporated, and Aaron will show you what that looks like. So this is the stage 1. You can see we have 2D data and then 1,000 groups and 14 integrations. You can see the glow stick superimposed on the cloverleaf pattern that shows nice centering. Then we have collapsed the groups axis, the 14 integrations. You can see we're starting to get nans from the data quality because we're doing error calculations and bad pixel processing in the background. Stage 2, we've subtracted the background. The glow stick has been removed. Stage 3, you can see the coldest ever imaged exoplanet popping out in the stage 3 data product. This dark inverted PSF was a background object that was in the reference image. So that's the data. What are important things to think about when you are preparing your proposal? We have the best resources, JDocs. There's a page of recommended strategies, a page of issues to be aware of. The best resource, frankly, is previous programs. Here's a list for reference later. I've emphasized 2 that are particularly instructive cases. Some of these, regardless, not making any judgment on the quality of the science or whatever, but these APT programs are just particularly easy to follow. So I would recommend these to look at. But this is a list of all the ones that we have run so far. Here's an example of how you specify your reference targets, your science targets. How do you tell which study to use as a reference? So I'm moving fast because I really want to make sure we have time for spaceKLIP. You set your PA range and the special requirements, sequence them. Okay, and so this is APT. You can also contact us. We're happy to work with you on your APT program. Known issues that you especially have to worry about for MIRI: these glow sticks are terrible. They're especially bright at 15 microns. And it's not just the glow stick across the quadrant boundary. It has a lot of structure. It's all over the subarray. Because of this, we require that everybody has to take backgrounds. And the backgrounds are unfortunately very time consuming because they have to match the exposure specifications in groups and integrations. And this is because of there are transient issues in the MIRI readout. So that depend on the number of groups and number of integrations. So if you match those, then your background will remove those transits exactly. And actually, the backgrounds, having dedicated backgrounds solves a number of issues with MIRI data. There's readout noise, there's other sources of noise, patterns that are superimposed on the data that get removed by taking contemporaneous background. So you get rid of the glow sticks, you lose, so there's overhead, but it does a lot to improve the quality of your data. We're looking at ways to take this burden off of the users, that we can do this background glow stick removal for you. But at the moment, the best results come from contemporaneous backgrounds where the glow sticks match the thermal environment of the telescope at the time of the science observations. They're public. If you want to experiment with yourself, I have links for you and also keywords for how to pull them from MAST. TA, target acquisition, we also have limitations on target acquisition. Because of the glow sticks, we were only able to commission some of our TA filters and some of our TA quadrants. Basically, you can only, right now we're only allowing TA from the upper right quadrant in each of the chronographs. And with the neutral density filter, you can use any of the chronographs, but the 10 micron filter is only available for the 1550 chronograph. The 560, we're commissioning it now for the 1140 and 1550. Basically, the deal we made with commissioning is that we would get take care of the most common use cases. And if someone has a special case, they propose anyway, and they'll come to us and we'll figure out how to make that filter work before their observations execute. So prepare your science, do whatever you need to do, and we'll figure it out. Come to us after your proposal gets accepted, and we'll figure out what we need to do to make your observations happen. The last thing is that if you want to do an offset TA, it's a little tricky to compute the slew. So this is let's say your target saturates all the TA filters, and so you have to use a nearby star. Basically, we have tools. We have a lot of experience with this by now. Tell us early so that we can start preparing your observation, because it requires a lot of planning. Here's a list of resources, some handy links. This is a library on ADS of all the chronograph science papers that have been published so far, and some other technical papers about how MIRI works that you might find useful. And then some highlights at the end that you can look at later.